I became interested in finding the points on the graph for body 1, this graph right here, that correspond to the points on the graphs for bodies 2 and 3. So this graph right here for body 2 and this graph right here for body 3. Now comparing bodies 2 and 3 is easy because they are just horizontal translations of each other. So all of the distances correspond. So this distance right here on body 2 corresponds to this same distance in body 3. So these points are corresponding points. These points are corresponding points. These points are corresponding points. But for body 1, this graph is shifted up 10 4/10 feet to the right. Remember, time starts 10 4/10 feet to the right of its point 0. So its point 0 is right here, shifts up 10 4/10 feet. Furthermore, it shifts another 85 hundredths of a feet when compared to bodies 2 and 3. Because remember, for bodies 2 and 3, that body travels past point 0, 85 hundredths of a foot, so it just travels a tiny bit past point 0, turns around, and then returns to its point 0, which is right here. Travels past point 0, 85 hundredths of a foot past point 0, turns around, and travels to its point 0 right here. So because of that shift, when you travel 100 feet out from point 0, here's point 0 for body 2, point 0 for body 3, travel 100 feet out for both of those, the corresponding point for body 1 has been shifted. So it's true that this is 100 feet from its point 0, but the corresponding point on body 1 is right here. It has been shifted, this 10 4/10 feet, plus another 85 hundredths of a foot. So here's that 85 hundredths of a foot right here from rest. So it's easiest to measure it from rest. So it's 85 hundredths of a foot from rest. So you have to shift body 1 to the right 10 4/10 feet, and then another 85 hundredths of a foot to get to the same corresponding point. So that's a total of 11 25 hundredths feet right to here. So 10 4/10 feet plus 85 hundredths of a foot, that's 11 25 hundredths feet. So now if I travel 100 feet from this point, I'm going to get to here, plus I have to add that 10 4/10 feet to right here, and then another 85 hundredths of a foot to right here. So that is at 111 25 hundredths feet. I'm going to show you that calculation in just a moment. I'm going to go over these graphs, but it's right there, 111 25 hundredths feet from its point 0. Its point 0 is right here. Go up 111 25 hundredths feet right to here, and the corresponding point for body 1 is right here. So at that corresponding point, the velocity for body 1 will be the same 8 98 hundredths feet per second. So this has to move faster. This instantaneous velocity, you have to find the point where it's moving faster, where it's moving 8 98 hundredths feet per second. And that is right here. I found it easiest to measure from rest for each of these. So from rest, to get 100 feet out from its point 0, which is right here, from rest, you have to add that 85 hundredths of a foot for both bodies 2 and 3. So you add that, 100 feet out from its point 0 is 185 hundredths feet from rest. 185 hundredths feet from rest. So all I have to do is measure 185 hundredths feet from this rest right here, and I will get to its corresponding point. To do that, I'm going to add the 89 6/10 feet from its time 0 and at rest. This is 89 6/10 feet. And so now I have to add this 10 4/10 feet. So if I add that 10 4/10 feet, this is now 100 feet from rest. Here's rest right here. This is 100 feet from rest, but at the same time, it is 110 4/10 feet from its point 0. So here's point 0, I'm going to go up 100 feet plus another 10 4/10 feet. So that point right there is 110 4/10 feet from its point 0. But then you have to add another 85 hundredths of a foot. You have to add this little piece right here, because remember, it goes past point 0, 85 hundredths of a foot. So you have to add that to this distance. So this is 85 hundredths of a foot. You add that up here. So this total distance from point 0 for body 1 is 89 6/10 feet plus 10 4/10 feet plus 85 hundredths of a foot. So it is 185 hundredths feet from rest, but at the same time, it is, here's the 100 feet from its point 0, 10 4/10 feet, 85 hundredths of a foot. So from its point 0, it is 111 25 hundredths feet. And that's the distance you want to use in the distance equation for example 1. You want to know how far that body is from point 0. So one more time, 89 6/10 feet from rest, plus another 10 4/10 feet from rest. That's 100 feet from rest to get to right here. Then you have to add another 85 hundredths feet. This is 185 hundredths feet from rest, but it is also 111 25 hundredths feet from its point 0. So you use that distance, 111 25 hundredths feet from point 0, in the distance equation to figure out the amount of time it takes to travel from rest right here out to here, which is 111 25 hundredths feet. And that time is 22 46 hundredths seconds to go from this point at rest and time 0, travel 22 46 hundredths, you get out here, and that instantaneous velocity. So you use that time in the first derivative of the distance equation, which is velocity. Use that time in the velocity equation, and the velocity is 8 98 hundredths feet per second, which matches this 8 98 hundredths feet per second and this 8 98 hundredths feet per second. So these 3 points are the corresponding points on the graphs because their velocities match. Using this arrow diagram, looking at example 1, this distance from rest is 89 4/10 feet from rest to get 100 feet from point 0. But I want the distance from rest to be the same as example 2 and example 3. So that means I have to add this 10 4/10 feet. So now I'm 100 feet from time 0, which is also from rest, and I'm 110 4/10 feet from point 0. So I've added this 10 4/10 feet. In addition, remember this example 2 and example 3, the body moves 85 hundredths of a foot past point 0. So I have to tack on this 85 hundredths of a foot right here. So now I'm going to be 185 hundredths of a foot from rest and time 0 this way, which means it's going to be 111 25 hundredths feet from point 0. You have to tack on the 10 4/10 feet and this 85 hundredths of a foot. So 89 6/10 feet from rest for example 1. But I want that distance to be 185 hundredths feet. So add the 10 4/10 feet. So that's now 100 feet from rest, but at the same time it's 110 4/10 feet from point 0. So 110 4/10 feet from point 0, but then you have to add the little teeny tiny 85 hundredths of a foot to that total. This little teeny tiny 85 hundredths of a foot right here. So now I would be at 185 hundredths of a foot from rest for example 1, and at the same time 111 25 hundredths feet from point 0 for example 1. And that's the distance you want, 111 25 hundredths feet. You want to figure out what the velocity is that many feet from rest. Now the confusing part is it's that 111 25 hundredths feet from point 0, but it's 185 hundredths feet from rest. So the equation, you use the 111 and 25 hundredths feet, but the distance from rest is 185 hundredths feet, which is the same as example 2 and example 3. I put this information in a table to make it easier to follow. So here we have examples 1, 2, and 3. And so time from point 0, time from rest, time from time 0. So this is when the timer actually starts. The distance from point 0 and the distance from rest. And down here is a summary table, examples 1, 2, and 3, when the velocity is the same for each example. So 8 and 98 hundredths feet per second. That is 111 and 25 hundredths feet from point 0, 100 feet from point 0, and 100 feet from point 0 for example 3. The time it takes to get there is 22 and 46 hundredths seconds for example 1, 14 and 96 hundredths seconds. This is from time 0 for example 2, and 29 and 96 hundredths seconds again from time 0 for example 3. So beginning with distance from point 0, this is the distance that gets plugged into the distance equation for each of the examples to get the time that it takes when the timer starts. So 100 feet for example 1 takes 21 and 17 hundredths seconds to get 100 feet out from point 0. Remember, that body for example 1 only travels 89 and 6/10 feet because it's moved to the right 10 and 4/10 feet before the timer starts. For example 2, 100 feet from point 0 takes 14 and 96 hundredths seconds, and that body travels a little bit farther than 100 feet because remember it has to travel that extra 85 hundredths of a foot, so it travels 185 hundredths feet from rest. Example 3, 100 feet. It's going to take 29 and 96 hundredths seconds to travel that 100 feet, but that's traveling 185 hundredths feet from rest. So 89 and 6/10 feet from rest, 185 hundredths feet from rest for examples 2 and 3. So let's look at this graph just for a moment. I'm going to zoom in on this section right here. So the time it takes body number 1 to travel 100 feet from point 0, it takes this 21 and 17 hundredths seconds right here. A little bit less time it takes to get to the corresponding point for examples 2 and 3, which is this point right here. So it doesn't take quite as much time to get 100 feet from point 0. The time it takes from point 0, for example 2, so here's point 0, has to travel this amount of time, and this is before the timer starts. And so it's traveled a little bit of the distance. The timer finally starts, so it doesn't take very long. It only takes 14 and 96 hundredths seconds to get 100 feet out from this point 0. For example 3, the timer has already started. So the timer is going. So it's going to seem like it takes more time, for example 3, to get 100 feet out from this point 0. So the amount of time from this point 0 has already taken this amount of time. So now it's taking more time. So now it's traveling that 100 feet from this point 0. So it's traveling out. It's going to travel farther. And so this is the time it's taking right here. And by the time it gets to 100 feet out from this point 0, it takes 29 and 96 hundredths seconds to get there. This is 14 and 96 hundredths seconds for example 2, 29 and 96 hundredths seconds for example 3, and 21 and 17 hundredths seconds right here for example 1. Here's the 21 and 17 hundredths seconds, 14 and 96 hundredths seconds. So it doesn't take as long because the timer hasn't started yet. And 29 and 96 hundredths seconds takes longer because the timer started early. The amount of time from rest differs. So for example 2, remember the timer was delayed 7.5 seconds before it started. So the timer started at time 0, but it had reached rest 7.5 seconds before that. So you have to add that 7.5 seconds to this 14 and 96 hundredths seconds to get a total time from rest of 22 and 4600 seconds. So in example 3, the timer started before the body had come to rest. So it started 7.5 seconds before the body came to rest. So you have to subtract that time. So the timer started, body comes to rest, moves out 100 feet to the right of point 0. So you have to subtract this time. It got added onto it. So that's 7.5 seconds taken away from this 29 and 9600 seconds. So the total time from rest is the same. For example 2 and example 3, it's 22 and 4600 seconds. Now in both cases, that's 100 feet from point 0, and it's 185 hundredths feet from rest. Remember, you have to add that tiny 85 hundredths of a foot to each one of these. Now from example 1, it takes 21 and 1700 seconds from rest, because rest is at the same time that the timer starts. So that body travels 100 feet to the right of point 0, but only travels 89 and 6/10 feet to the right from rest. Remember, it's moved 10 and 4/10 feet to the right from rest, and it's 11 and 25 hundredths feet from rest, less than example 2 and example 3. So for example 2, the timer was delayed in starting. So the timer has not started yet, has not started yet, has not started yet. And the timer starts now. So the total time, you have to add this 7.5 seconds to this time right here to 14 and 9600 seconds. So that total time is 22 and 4600 seconds. Add this 7.5 seconds plus 14 and 9600 seconds. For example 3, the timer starts now, and it started early. So this is time before the body reaches rest. And so finally it's now at rest. So this is 7.5 seconds before. So this is an extra 7.5 seconds that has to get subtracted from the amount of time that body takes to get 100 feet from point 0, or 185 hundredths feet from rest. So now the body started to move to the right, and it continues until it takes 29 and 9600 seconds. But you have to subtract this 7.5 seconds right here. So the time from rest is that same 22 and 46 hundredths seconds. So from here to here is 22 and 46 hundredths seconds, because you subtracted the 7.5 seconds. And for example 2, it's from this point here at rest to here. That's a total time of 22 and 46 hundredths seconds, because you've added this 7.5 seconds right here. From rest, for example 1, it takes just this 21 and 1700 seconds, because it's traveling a shorter distance, to get 100 feet from point 0. So for example 2, you have to add that 7.5 seconds. 100 feet from point 0, 185 hundredths feet from rest. For example 3, you have to subtract that 7.5 seconds. 100 feet from point 0 and 185 hundredths feet from rest. In example 1, the timer starts at point 0, but it doesn't travel as far, so it takes less time, 21 and 1700 seconds. For time from point 0, for example 1, it's the same. It's the same amount of time from point 0 to move 100 feet to the right. It's the same amount of time from rest to move 100 feet to the right, and the same amount of time from time 0 to move 100 feet to the right, because all three of these are at the same spot, the same point at the same time in the graphs. Time 0 is the same as rest, is the same as the position of body 1 from point 0, which is 10 and 4/10 feet to the right of point 0. So all three of these are right here. So here's example 1, body 1 at rest at time 0, and its position compared to point 0. Remember, it never intersects point 0, so that creates a little bit of confusion. So you have to position body 1 at 10 and 4/10 feet to the right of point 0. So all three of those are at the same point. So it takes that same amount of time, 21 and 1700 seconds, to get 100 feet out from point 0. right here. That's this 21 and 1700 seconds. So zoom in just a tiny bit more. The time from point 0, so it's 10 and 4/10 feet to the right of point 0. So the time it takes to get from here 100 feet out is this 21 and 1700 seconds. For examples 2 and 3, each body does intersect with point 0. And that time that it takes to travel this 100 feet to the right of point 0 is a little bit less time than it takes to travel from rest. A little bit closer at point 0 to 100 feet out than it is at rest. Remember, from rest, it has to travel 185 hundredths feet. A little bit of extra distance, that 85 hundredths of a foot, to get 100 feet out from point 0. So a little bit extra distance has to travel a little bit extra time, but from point 0, it's a tiny bit less than that. So for example 2, instead of adding 7.5 seconds, you have to only add 5 and 44 hundredths of a second to this time measured from time 0. So here's body 2 right here. So this is 7.5 seconds from time 0. So you have to add that 7.5 seconds for rest, but from point 0, it's a tiny bit less time. It's actually 2 and 600 seconds less time. So this time from here to right here is 2 and 600 seconds. So this is example 2 right here. So you have to add this extra 5 and 44 hundredths seconds to 14 and 96 hundredths seconds. So that's a total of 20 and 40 hundredths seconds to travel from this point 0 100 feet out, which is right here. From rest, you have to add 7.5 seconds. From point 0, you have to add 5 and 44 hundredths seconds, a little bit closer. So a total time of 20 and 40 hundredths seconds. And it's the same for example 3. You have to subtract time because the timer starts early, so you have to subtract that time. For example 3, from rest, you have to subtract 7.5 seconds. And for example 3, from point 0, you actually have to subtract more time. It's 9 and 56 hundredths seconds to calculate how long it takes from point 0 because the timer had started early. So this is example 3. The timer starts early, so you have to subtract the 7.5 seconds from rest, but then it continues, and now from point 0 you have to subtract a little bit extra time. So it's 9 and 56 hundredths seconds that you have to subtract from 29 and 96 hundredths seconds for example 3. So from rest, zoom in on this a little bit more. From rest, you have to subtract this 7.5 seconds because the timer had started early, and you have to subtract a little bit more than that, so it's 2 and 600 seconds more. So this is 9 and 56 hundredths seconds right here. You have to subtract that from 29 and 96 hundredths seconds out here. And so the time it takes, example 3, from point 0 is 20 and 40 hundredths seconds. So it travels from point 0, it's moving towards 100 feet, and it just continues out here to get to this point here. That takes 20 and 40 hundredths seconds, or 20 and 4/10 of a second. So you have to subtract that 9 and 56 hundredths seconds from 29 and 96 hundredths seconds. This is the value when you use 100 feet in the distance equation. This is the time that you get, but that time, the timer has started early. Now, so 9 and 56 hundredths seconds and 5 and 44 hundredths seconds are solutions to the quadratic equation for distance for example 2 and example 3. So that graph goes through distance 0 at 2 different times. A negative 5 and 44 hundredths seconds and a negative 9 and 56 hundredths seconds for example 2, and a positive 5 and 44 hundredths seconds and a positive 9 and 56 hundredths seconds for example 3. So 9 and 56 hundredths seconds negative, a negative 5 and 44 hundredths seconds for example 2. So 2 different times body 2 is at point 0, and 2 different times body 3 is at point 0, at a positive 5 and 44 hundredths seconds and a positive 9 and 56 hundredths seconds. And you take the right solution, the solution that's farthest to the right in each case, because the velocity is positive at that point as it moves out from rest through point 0 towards 100 feet out. So from rest through point 0 and 100 feet to the right. So one last time for example 2, this was negative time. So you have to add that time to calculate how long it takes from rest and from point 0. So it's slowing down, slowing down, slowing down, comes to rest, turns around, moves out to the right. So the velocity is positive right here as it moves 100 feet out to the right. So you have to add this time. For body 3, you have to subtract this time because the timer starts, comes to rest. So you have to subtract that time to measure how long it takes from rest 100 feet out. It starts back to the right, positive 3 feet per second. When it gets out here, this is 7.5 seconds from rest. This is a negative 3 feet per second as it's coming to rest, slowing down, slowing down, slowing down, slowing down, turns around, passes point 0, moves out to the right. It's traveling towards 100 feet to the right, but at this point, same time from rest, only traveling away from point 0 or away from rest. This is traveling at a positive 3 feet per second. So if you look at the graphs of the velocity equations for each example, each of these equations has a slope of 4/10, because that's the acceleration, 4/10 feet per second for each second. So 4/10 feet per second squared, or 4/10 feet per second. So the velocity is increasing 4/10 feet per second each second. So for example 1, at time 0, example 1's at rest, and 7.5 seconds later is traveling at 3 feet per second. So this is 7.5 seconds right here. So now it's traveling at a positive 3 feet per second. It's 4/10 of a foot per second, which is 2.5 seconds to increase its speed by 1 foot per second. So 2.5 seconds, 1, 2.5, increases its speed 1 foot per second. This is 1/2, 1, 2, increases its speed another 1 foot per second, and 1, 2.5, increases its speed another 1 foot per second. So this is at 3 feet per second. For example 2, at time 0, it's already traveling 3 feet per second. So here it is, 3 feet per second. It was at rest 7.5 seconds earlier. So that's right here. So 7.5 seconds earlier, example 2 is at rest. 7.5 seconds goes by. Now it's traveling at 3 feet per second, and it continues on to the right as it travels towards 100 feet to the right. For example 3, at time 0, when the timer starts, this body is still slowing down. It's traveling at a negative 3 feet per second at time 0. So it's slowing down, slowing down, slowing down. So as time goes by, it's still slowing down, and it comes to rest at 7.5 seconds after the timer starts. So this is 7.5 seconds after the timer starts, comes to rest. It's turned around, and now it's traveling to the right towards that 100 feet to the right. Example 2, the body has slowed down right here. It's come to rest, turned around, and now it's traveling towards the right. At time 0, it's traveling 3 feet per second. Example 1, this body is slowing down, slowing down, slowing down, slowing down, and comes to rest at time 0, and now turns around and is traveling towards the right with a positive velocity. And example 3, slowing down, slowing down, slowing down. This is time 0 right here, but it's still slowing down. Comes to rest after 7.5 seconds after the timer starts, and then turns around and heads out to the right. Slowing down, comes to rest, turns around, the timer still has not started yet. So 7.5 seconds after rest, the timer finally starts. Timer starts, still slowing down. So this is a negative 3 feet per second. This is a positive 3 feet per second. Slowing down, and 7.5 seconds after rest, right here, now it's at positive 3 feet per second. So example 2 times 0 is 7.5 seconds before example 1 times 0, and 3 feet per second is traveling at 3 feet per second compared to 0 feet per second, and it's 15 seconds. So it's 7.5 and another 7.5 seconds. So this is 15 seconds before example 3, and it's traveling 6 feet per second faster than example 3 at time 0. So 7.5 seconds before example 1. So here's the 7.5 seconds before, and 3 feet per second faster than example 1, 6 feet per second faster than example 3, and 15 seconds before example 3 reaches this same velocity out here at 3 feet per second. This table shows both the time and the distance to travel on each graph that the body has to travel to reach a velocity of 8 and 9800ths feet per second. So I already covered the distance for body 1 of 111 and 2500ths feet. Just a quick review. If you add 89 and 6/10 feet from rest and the 10 and 4/10 feet from point 0, and the small 8500ths of a foot that gets added because examples 2 and 3 go a little bit past point 0. Add those three together, that's the 18500ths feet from rest. And then from point 0, you have to add this 10 and 4/10 feet to get you out to 111 and 2500ths feet. So 100 feet plus 8500ths of a foot, that's from rest to this point right here. And then you have to add this 10 and 4/10 feet right here to figure out the total distance from point 0. Once again, 111 and 2500ths feet. So using this distance in the distance equation for example 1, you'll come up with 22 and 4600ths seconds for the time. So it takes this amount of time to travel 18500ths of a foot from rest. And that would be 111 and 2500ths feet from point 0 to get to this velocity of 8 and 9800ths. And this time has to match the time that it takes for bodies 2 and bodies 3 to travel from rest to 18500ths of a foot. This distance right here out from rest, this 22 and 4600ths seconds, has to be the same for body 2 and body 3. So 22 and 4600ths seconds from rest for body 1, 22 and 4600ths seconds from rest for body 2 right here, and 22 and 4600ths seconds from rest for body 3 right here. For example 2 and example 3, that gets you out 100 feet from point 0 and 111 and 2500ths feet from point 0 for body 1. All three now are traveling at a velocity of 8 and 9800ths feet per second. Now for body 2, from time 0, you have to add the 7.5 seconds. And for body 3, from time 0, you have to subtract 7.5 seconds. So body 2, you have to add the 7.5 seconds right here to time 0. And for body 3, you have to subtract this 7.5 seconds right here from body 3 from time 0. Now I knew the velocity for example 2 and example 3. I knew that it was 8 and 9800ths feet per second, and I wanted to find where that point is for body 1 or example 1. So I could have just used that velocity and figured out the time it takes to reach that velocity of 8 and 9800ths feet per second. So to reach this velocity of 8 and 9800ths feet per second, how long does that take? You just divide by 4/10. So that's the same as multiplying by 10^4. So 10 times 8 9800ths is 89 and 8/10 divided by 4. That equals this amount of time, the 22 and 4600ths seconds. And then use that time in the distance equation. So how far does that get you? How far do you get in 22 and 4600ths seconds? You get 111 feet and 20, this is 2900ths, a little bit of rounding, difference in rounding. So it's 111 and essentially 2500ths feet. So I could have used this first, or you can just use this as a check. So the corresponding point at this velocity is 111 and 2500ths feet from point 0, 100 feet from point 0, and 100 feet from point 0. The time it takes to get there, 22 and 4600ths seconds from time 0, 14 and 9600ths seconds from time 0, and 29 and 9600ths seconds from time 0. These two times right here. And then example 1 is this time right here. Example 1, it has to move a bit farther, 11 and 2500ths feet, to get to this velocity. So a little bit farther, has to take a little bit more time.